primarily for the optimization. So what the autoencoder, first, what does it mean, autoencoder? It means, auto means self, so encoding itself, that's the intuition. And so an autoencoder at its basic is just a feed forward. It is, an autoencoder is a multi-layer perceptron. It's a feed forward neural network. It's just that it has been architectured in a certain way, and also the losses will be slightly different, and also sometimes it's trained layer by layer. So, but generally, like at inference time, at the time of inference, it is a multi-layer. It's a feed-forward network. It's a so the output of the network will be the prediction. Will be how well could you recreate your input? That's the idea here. And so that's what the output, or what I call usually in MLP the score function, but the output will be the original input. And so, and we'll split it in usually in two parts, the encoder and the decoder. And a classic, although it's not required, but classic autoencoder will have more of a hourglass where information comes to this middle layer, which intermediate layer that usually is a lot smaller with number of neurons, that forces aggregation and fusion of information. And then you will have this decoder that will then try to, from that summarized information, be able to regenerate the initial. And if you look at it, this is not far from the word-to-vec. This is one difference is that in the word-to-vec, we were not trying to recreate yourself, but in fact recreate the context, but the similar architecture to that. Often in autoencoders, they will also share or tie the weights between it, and that will also help because that way, however you regenerate the data should be related to how you however you decode or generate the data. It should be related to how you encode it. Also, it could be seen as the intuition in the brain. There's some famous result that says that the way people perceive speech is related also to the way they generate speech. So you could also intuitively come it from a cognitive science perspective. So this is the basic of autoencoder. I just want to add one more thing about autoencoder before I get to the multimodal, which is how do you define the loss in this case? And the loss can be different. It could be, there's different versions, but the key aspect of it is that you will compare usually your input with the output simply by hoping that they are as close to each other. Sorry for the small typo. But how to make it more robust to noise. There was this nice little, nice cute extension to it, which is called denoising autoencoder. And the idea here is that I will not look at the input itself, but add a noisy version. So not the input itself, but look at a noisy version of it. And so the network will go from the noisy, and then the loss will be trying to get the original version of that. So, so the network will be learning from this, but the loss will be from the original version, that getting as close as possible. And that will be usually bring matter. Often people just talk autoencoder without talking about the denoising itself, but it's a nice trick to be had. But let's talk about multimodal. So how can you make this option autoencoder multimodal? Think about it for a second. How can I take this idea of autoencoder and make it so that I can learn a multimodal? So this is maybe, or at least one of the ideas you had. This is a bimodal autoencoder, and one of the key aspects of it is that it does joint representation or shared representation. Okay, so joint representation, which is different from coordinated. We'll talk next week, not next week, on Thursday. But here is joint representation. What it means is, and how will you train this joint representation? One thing that they maybe don't always say explicitly, but is very important, is, and many of these, is that you need paired data. You need data between the two modalities. You need to have this data. So I have my audio and I have my video, and I need to be able to pair. So I need that paired data. So in the case of audiovisual speech recognition, it will be maybe the video with the, or maybe just the lip tracking, the tracking of the lips. In this case, I think it was not the raw video, but they look at the lip shape. And then you have the audio. And again, they will probably not take the raw audio, but instead use spectrogram or some other representation. And then what it is the goal is to go and encode the representation. And so I get this both inputs, and then I find this joint representation. And then also what's very challenging also from that joint representation inside it, there's a need to have enough information in it to be able to regenerate video and regenerate audio. So as you can imagine, this is very challenging because the shared representation needs to include enough information to regenerate both of them. But if you can and learn this, and the initial results were pointing that way, one little thing that they did that was somewhat important is that the initial layers of these encoder and decoder, and these layers and for the video were already pre-trained. You often will do that also. You may pre-train this, and in this case they pre-trained it with a typical autoencoder. And then once you pre-train that, then you can train and use both together. And that's the usual way. You train the model to reconstruct both modality. But what's really cool once you've done that, so you train, you pre-train this, and then you train together. And then what's really cool after that is that you can go and remove one. What will happen? And it's a little bit, we talk about the blue car. I mean, that would have been the other idea. Like I have an image and a caption, and I learn it together. Video representation, that joint representation, I should be able from it to be able to sample video, but also I should be able to generate and sample audio. And it's really cool. I can in fact remove video as well from it. So these are very interesting aspects of the autoencoder that comes from this extension. It can be now even discarded. You can completely, so one thing you can do is completely discard the decoder. And now let's say you have my video and my speech, and I want to learn a new task. Let's say it is speech recognition. So I'm trying to predict language, like the words, the spoken words. I can use now my shared representation to also recognize language. And then I can do some cool thing. So at training, I could train. So I pre-train. I pre-train with this way. With in fact, not this way, but completely this way. So I pre-train this way. But then I fine-tune it for the class of predicting words. Okay, so I do speech recognition. Here that was speech, this is video. And in my first version of the training, I had both audio and video. But in my second stage, I only have audio and language. And then at test time, which is, this is a co-learning kind of scenario. At test time, I don't have audio, but I can go ahead. And because I had trained earlier in the pre-train, I had pre-trained also, I will be from video able to read lip reading. Really cool, no? I mean, the results. I mean, it was early on, and there's a lot that followed up this, but I thought was really cool. I wanted to also discuss, although mathematically I'm not talking yet about a restricted Boltzmann machine. I want to talk about the results of that paper, because the results of the paper was really cool. And these are two of the, I will say, landmark papers in the neural multimodal that really started a lot of work. In this case, they didn't look at speech recognition, they look at image and text. And what they do is that when you have a generative model like IBM, what they can do is that you get your initial representation of the text. Let's say for now, let's call it word2vec. So I get my word2vec here, and the image is like maybe the output of a CNN. And then what will I do? I will learn a first layer. So this will be trained together. And this generative model, because these maybe have a lower, smaller number of neurons, then I will start summarizing a little bit the image. And on this side, I will start summarizing the text. And then I will train now the second layer, And then the interesting one is to train the joint representation. And in practice, you will make it so it's almost, you can also do it step by step, or at the end, you can also do it like end to end. But what's really interesting is now what do I have? I have my input on both sides, and I have 5 intermediate representations. I have an intermediate representation here, intermediate representation, and the information can flow both ways because generative, and in this case, it can go both ways. And so it will be really interesting to say, I mean, I hypothesize that the middle representation is the most, like, that's the most intermediate, but there's nothing that forces it. Maybe this one is really the intermediate, the middle point, or maybe this one is the middle point. And so that's one question that you have. The training for that is variational approaches. And so, and as I mentioned, we'll discuss more the training. But the result, I'm going to come back to the results. I want to show you this graph. What's really interesting is that it's the middle, and the comparison between the two is not as important as the let's just look at the red one. What's really interesting is to see how much information, how successful the task that we have is, I think, multimodal image retrieval, and the idea would be maybe the middle is the best, but what was really interesting is to see the asymmetry between this, the fact that text was different from the image. Although the two together are really useful, you can see that there's an asymmetry between them, and somehow this one gained a lot from the image. So the text very quickly gained a lot from the image, but that was different on the other side. So it's interesting to look. Like often we only talk about one intermediate representations, but in some models, in these generative models, you can start looking at the flow of information between that. And so the task here, you can pre-train on unlabeled data. It's unlabeled, but really there's some supervision, which is there's pairing of data. I mean, you have paired data. And then when you do what the unsupervised task, then you can do these things where you have an image as input, and then you can see the generated tags and compare with the ground truth tags, or the opposite, you have a text as input, sample images from that text. And so you can, it's a fully generative model, so both ways. And so that's the beauty of this model. And then it can be used on a prediction task. So, and that was what the graph I was showing also is that, so you train originally, pre-train unsupervised, but then you train it on visual. And the beauty of it here, and I should have mentioned, is that the only real goal is vision. Okay, so I'm going to now show you the same graph. Here, the prediction, here this prediction is only using the input of visual input. And so if you use just vision and you never only use that representation of vision, but then if you start adding and then you can see, but then eventually it gets a little worse with the going in the other direction. So it's also interesting to see the asymmetry on both sides. So, okay, this is the generative models that I wanted to discuss. I wanted to also discuss the supervised cases for this multimodal. The supervised case, the idea is that maybe you have a pre-trained representation, but also sometimes you may want to train right away end-to-end for a taskless sentiment. And so the joining of the unimodal representation, it could be simple concatenation like I've shown here. You could multiply the two, like you can multiply HX and HY, or learn a multi-layer perceptron from it. I showed the multi-layer perceptron. But when you do this joint representation, and that's also true with the unsupervised case, but I'm going to show here, is that there is a lot of information that sometimes is unimodal, but sometimes there's complementarity between two modalities, and there's this nice bimodal information. And sometimes there's also complementarity between three modalities, and so we call this trimodal interaction. And so we want to be able to learn these joint representation, but also being able to model bimodal and trimodal interaction. So let's say you have to, in the case of sentiment, you have only what I say, how I say it, the audio, and also my vision. So the simple will be just a concatenation and a neuron on top of that, neural network on top of that. But as I said, there's unimodal, bimodal, and trimodal. And let me give you an example. Like if I say this movie is sick, is it good or bad? It probably may be good, but neutral. It's a bit ambiguous, specifically in US. This movie is fair. It's probably positive or neutral. Smile, probably I'm more on the positive side. But if I'm loud, hey, I can be loud and positive or loud and negative. But let's look at bimodal. This movie is sick and I smile. Then it's quite likely that I'm very positive. Or this movie is sick and I frown. Then it's really most likely negative. But this movie is sick and I'm loud, still ambiguous. That's why sometimes you look at trimodal interaction. And in trimodal interaction, then this movie is sick, I smile, and I'm loud. Very positive. And I will say the job of multimodal fusion would have been super easy if it was just this kind of example, almost additive, like fusion is additive. But the fusion process is a nonlinear process. As you see here, this movie is fair. Even if I smile, I'm loud, there's fireworks, everything. Because in this case, language takes over the other modalities. And then that means that you should not simply go and simply go ahead and just add to each of them. No, in this case, language took over the others. And so this kind of nonlinearity is important to be modeled in your model explicitly. And so there has been some very interesting ways to approach it. One nice simple way is called bilinear pooling. And so when the pooling, instead of doing just an average pooling, so I have HX and I have HY, and how I bring it together, I could just average pool them, like just, but here, the idea is to do the product, cross product in such a way that you end up with this matrix. And it's really nice because now suddenly what you have is for each element here, you get those bimodal interactions. So this point here is related with this. So this one is telling you how are dimension 1 of HX and dimension 2 of HX, like this looks at this kind of interaction. So if for sentiment purpose, this interaction is really useful, then this neural network here can go and start putting more emphasis on it. Or maybe it's the third one from X and the second one from Y, then this one will be taken. So it's nice because you're kind of exhaustively looking at all possible interaction. This is bilinear pooling, and there was a nice, neat little extension. The bilinear pooling will be, you can go symmetrically. But then there's a small little extension to that, which goes ahead and add this little one to it, like this little one here to the bilinear pooling. It's a very simple idea here. And by taking this little thing, what's really nice is suddenly in your matrix, in your response map here, what you get, what's really nice here is that you get both the unimodal and the bimodal. So what you had in the bilinear pooling plus the unimodal as well. And that nothing stops you from doing it in 3D. So now you suddenly have your unimodal, your bimodal, and your trimodal all within one. And what was nice in this is that this approach outperformed the, it was state of the art at that point, but more importantly, it outperformed the bimodal pooling as well. And what you're probably asking yourself, oh, but suddenly I have this huge matrix because suddenly I have this big tensors in your model, huge tensor. And so I have more parameters to learn. And then you have kind of this trade-off. And that's something I hinted at when we talked last week, no, 2 weeks ago, about basic of neural network, is sometimes neural network, it is useful to go larger to then go smaller. And so sometimes it is helpful, and that's what it seems to be hinting at in the experiment empirically, to go larger, because here I have more parameters than I had here, but I made it the problem simpler, because it's much simpler from a fusion perspective to just go ahead and pick the input that are the most relevant to my classification task. So although I'm increasing the number, I am making the problem easier. At least that's what empirically it seems to be showing. There is some nice extension you can do to say, hey, this is very big, this tensor, and I have my two modalities, and I have this big tensor, and so I'd like to make it simpler. And there is some nice work that was simply looking at it as a decomposition, where you decompose the weight. So instead of using the weight itself, you keep the step before it, and then you also decompose the tensor, and you rearrange them. And so this nice little animation. So you have this big tensor, and what you will do is decompose it. This is a CP decomposition. This is a well-established decomposition that any kind of matrix can be approximated this way, or tensor. And then I will decompose the Z as well, because I know that the Z, it's a matrix here, but the Z came originally from 2 vectors. And then I will just reshuffle things, and I will just rearrange things together. And by doing that, what's really nice is that suddenly I get this, which is a lot easier. Like now I can start adding another modality. I can add more and more modality, and it will scale better. One last representation I wanted to discuss, and then we'll talk about the concept of temporal, like how do you do multimodal and temporal, and give one example. But one other aspect which we discuss a little bit when we talk about applications of multimodal is earlier when we look at representation, we said, hey, text and image and you have paired data, and then I learned joint representation. But there's also the idea of translation. You can also learn a multimodal representation by translating from one to another. It is slightly different here than an RBM. The RBM was a generative model that allows to go both ways. But here, this will be a feed-forward network. And so the image could be a CNN, and the text will be some kind of embedding. And these days, you probably use BERT, but back in then, they could have encoded the language with Word2Vec and an LSTM on top of that. So this is another way to do this, and we'll discuss more these kind of translation-based approaches after probably more around week 7. I also want to discuss multimodal LSTM as an example, and as an example of temporal modeling. So because often when we talk about fusion, a lot of people they don't push for the temporal. So fusion, you could always, if you want, just highlight and say, hey, I'm only going to look at fusion locally in time. But what's interesting is so the simple way of doing fusion, and what I will say 95% of the time, people will do fusion at in a very simple manner from a temporal perspective. There will be maybe some interesting fusion locally in time, but then a lot of approaches don't think about the temporal aspect of the fusion and try to make it part of the fusion process. There was some interesting approach that I want to highlight just as an example. That's not the only way, but I want you to share, because we already discussed LSTM. We'll talk about more of those temporal fusion with transformers, for example, later. But I wanted to give you an example of doing it temporally. How do you do multimodal temporal? And the idea here is called multi-view LSTM. And so the multi-view LSTM, if you remember, one of the key aspects of an LSTM was that memory cell. Okay, this memory cell was useful for 2 things. One, because of the vanishing gradient that helped with this, but also it helped, and we had that forget gate to also help us, in a sense, remembering or forgetting things from time step to time step. So one interesting extension of it is to say, hey, if I have memory, and why not having more than one memory? So in the typical LSTM, I have only one memory, but what if I have, in fact, multiple memories? I have a memory for modality 1, a memory for modality 2, a memory for modality 3. So what is this? This is a lot closer to a coordinated representation. In fact, you could imagine this architecture, I could do it in such a way that the memory for modality 1 takes only the input of modality 1 and the previous hidden state of modality 1 and ignore completely modality 2 and 3. And if I did that for modality 1 and similarly for modality 2, I ignore modality 1 and 3. If I do this separately in that spectrum of like coordinated representation, I will be at the extreme, like completely like separate representation. So this is one way, extreme way. It's mostly it's exactly the same as having 3 LSTM separate, one for each modality. But it will be interesting to start looking and exploring what are the different ways I could coordinate between modalities. And the way to do this is the key aspect, the key moment to do this is at this moment where I create that input gate. At the moment of input gate, I will start exploring different ways to aggregate, because this is, if you remember, the input gate is the place where I take my previous hidden state and my new evidences. I take my new evidence and my previous knowledge and aggregate together to create the output of that input gate. And then this will go on. So this is the important moment, because that's the moment where I'm bringing together previous knowledge, prior knowledge with new evidences. And that seems to be a key, a perfect place to say, I will not look just about my previous evidence from my own modality and new evidence from my own modality, but I will also take advantage of the other modalities. And so you could imagine different topologies to do that. And for now, I'm only gonna look at for one modality. So for modality 1, what do I use? And to help decide what I aggregate, how do I aggregate knowledge from the other modality, I will say I will introduce 2 hyperparameters. One is how much from the current modality and how much from the other modalities. And so if I make it extreme, only my current modality and none of the other modality, then what does it mean? This is just 3 separate LSTM. And the other one is completely ignore what I did and only look at the others. And this is called coupled. And it's really interesting. There is a famous 2000, or maybe even before that, paper on coupled HMM. Coupled HMM. And the extreme version of that, it says you don't even have your knowledge. And what it means is that you're only going to get information from either from the other modality. And so that means that the other modality has to have enough knowledge to create your own modality. So the representation should be as informative as possible to create the other modality. And then maybe I couple again and I create so I can go back and forth like this. That's coupling. In practice, if you have 2 modalities, modality A is used for modality B for modality A, and then I do the modality B for A, modality A for B, and so like this. The alpha and the beta are 2 hyperparameters in that multi-view LSTM. So in the multi-view LSTM model, alpha and beta, although you could imagine now these days making them a dynamic gate in itself, but for now, so that means for the purpose of this is that alpha and beta are hyperparameters that are decided. And so if you make all of them 1 and both case, then suddenly you use both. So you mean the information from my modality and the information of the other. And then finally, you could do any of them. And as I just hinted at, you could make alpha and beta as just a gate like that is dynamically deciding how much do I trust myself and how much do I trust others. So I wanted to share this to be able to introduce quite a few concepts. One is view-specific information. One is coupled weight. This is one way to bring information from other modality. The specific of this algorithm is just one algorithm, but I want to explore that. And multi-view LSTM does improve on that. What we will do next week, and this is just a little preview for, not next week, but tomorrow, Thursday, we'll talk about coordinated representations. And coordinated representation, you learn through representation, but you coordinate. And I told you, this is a spectrum of things. And if your coordination between these two, left and right, like text and image, are so strong, like a similarity matrix, like a cosine distance. If you want the cosine distance to be as small as possible, as we've seen in embeddings, like with language embedding, if you force them to be as close as possible, you're mostly making it so that these are mostly the same, or at least their cosine distance is the same. So so this is in the spectrum of things, very, very strong correlation. But it turned out that some of the papers I talked to you about, and so what will be the loss function? And so one is to have it very strong, like a cosine similarity. There is another one, which is you have the two distance, and you could make it as a max margin, which is a little bit related to what's really popular these days as contrastive learning. But yeah, so do you want to get the positive? You don't care, or it's okay, but you want to make the negative, you want to pay a price for the negative cases. And that was, if you ask also one key papers one papers was the multimodal deep learning with autoencoder. You have the RBM one that I talk about, and this is another one, devise, or French way to pronounce it, devise will be to bring these two embeddings together. That was a simpler one. There's different kind of ways of looking at these, and that's one of the paper that I think this one I may have put as optional or not. I forgot if I put it optional or not. But is that there's ways to learn their embedding in such a way that you, in this case, you only focus on the negative example, but there's also structure preserving constraint. And the intuition here is you want image that share the same meaning to be close to each other, and then the others are outside. So it's kind of if you're close to each other, then you want the same meaning, otherwise it's not. So it's structure preserving because the structure meaning if you have some kind of similarity function or closeness or neighborhood, then you can use that to help in the learning. And one of the paper that we proposed was about extending the basic one to do that. So I wanted to share these different approaches. We'll talk more on Thursday about those different coordinated approaches and discuss different approaches like this. So thank you very much for your attention.